video to just do some quick review before my magnetism students. So we're looking at right now a ring inside of a magnetic field. Okay, and of course there is an area to that ring. So we'll just say the area of the ring, of course, is just simply pi r squared. So the radius of the ring. And of course, flux, okay, in this magnetic field, of course, is going to be BA cosine theta. Now, if we want to calculate the voltage generated by this, E, of course, is always going to be equal to the change in flux with respect to time. That's what it will always equal. Okay, now several things can change here. Now, what if we keep the angle constant and then we simply vary the magnetic field? Of course, then E in this case will be equal to the area and then multiplied by the change in magnetic field with respect to time. Now, of course, if we keep the magnetic field the same, and then this ring looks pretty solid, maybe we could then, rotate the angle. Okay, then. So in that case, our E, of course, is going to be BA. Okay, and then, of course, we're going to take the cosine of theta, and I'm going to take the derivative of this function. Okay, and of course we're going to end up with minus BA, okay, sine of theta times d theta dt. As we already know, theta dt does equal angular velocity. So we have minus b a omega sine of theta. Now we can write theta as omega times t. Why? Because if it's a constant angular velocity, that's what we got. Omega theta equals omega times t. Now, what would that look like if it was a graph, of course? Well, if in a graph, we're going to be just having a sine wave like this, right? Going around. The period of that sine wave, of course, is going to be from one location here to the next location here, t. Okay. So, of course, then omega does equal 2 pi divided by t. So if you have a graph of this thing, rotating through time, it'll make a sine wave, and then you can get omega t by just simply looking at the actual frequency of it. So that's pretty much what we're dealing with if you rotate something inside of a magnetic field. Now, of course, you could change the area of this if it was a flexible, I don't know, ring or what you want to call it, and then of course you would have b times dA dt if that were to happen. Now, another topic we've been dealing with, of course, is Ampere's law. So if we have a wire with current going upwards here, okay, of course, you can draw an Ampere's loop around that, okay, and we're remembering that the closed surface integral then, or not the closed surface, the line integral of b dot ds does equal mu naught, okay, times I enclosed. And of course, ds is around this entire circle here. So then we have b equals 2 pi. Well, it wouldn't be equals, it would be times, of course. It would be b times 2 pi. Okay, and it was, I guess we'll call that r equals mu naught I enclosed. So then b, of course, equals mu naught I over 2 pi r. Now, of course, as we go farther and farther away from that, we should see that the magnetic field then decreases by 1 over r. Okay, because r is on the bottom. So the farther I get away from the center of this wire, I expect that to to decrease, okay, by 1/r. So, you know, Ampere's law with symmetry is, you know, pretty easy for us to deal with. Okay, what about the next, you know, situation here? So, what if I wanted to look at the magnetic field at, let's say, at this location of this kind of circuit here? And of course, I could draw myself an Ampere's loop around that. Okay, and when we're looking at when we close this circuit, okay, current, of course, is going to go this way. But we're filling up this capacitor here through time. Okay, so at this position here, if we call this position R again, of course, we're expecting B to equal mu naught I over 2 pi R. Okay, but this time I, the current I is decreasing. It's going down. Okay, it's decreasing. Okay, therefore, if I stay at the same position here, magnetic field's not going down because of my distance from it. The current is going down as I fill this capacitor. So we expect magnetic field at this position to be going down because this capacitor, okay, is going up. Okay, let's take a look at another situation here. Again, we did this one in place. So let's say I've got a wire, a circular wire with current going in this direction like this. Okay, and I want to get the magnetic field at this position P in the middle here then. Well, this is going to be a Biot-Savart Law application. Okay, so Biot-Savart, of course, is going to be differential magnetic field, okay, dB, okay, so dB equals mu naught, okay, I dl cross r hat over 4 pi r squared. Okay, now let's identify a vector here to a dl here then. Well, the dl is always facing in this direction here and will always be perpendicular to our radius r. Therefore, our cross r hat is just going to be sine of 90. So that's 1. Now, dl, we could represent dl then as r d theta. Okay, so that makes it, you know, pretty easy for us to deal with. And then r, all the way as we go around, r is going to stay the same, so r squared. So when we're done, we'll have dB equals mu naught I dl, which is r, okay, d theta, and then our cross r hat is already sine of 90, which is 1, okay, over 4 pi r squared. So 4 pi r squared. Okay. So then when we're done, of course, dB is equal to mu naught I. Okay, and it looks like we have just a d theta on top then. And then over 4 pi r. Okay. Now, of course, to get the magnetic field, we'll need to integrate this. So we're going to integrate this, but now we're integrating around the entire circle. So this is going to be from 0 to 2 pi of mu naught I d theta over 4 pi r. Okay. And then you'll just integrate that, and of course, when we're done with that, we will of course have mu naught I over 4 pi r, and we're integrating this from definite limits. All we'll have then is theta from 0 to 2 pi. Okay, so then that becomes mu naught I. Okay, and of course, we'll just have 2 pi over 4 pi times r. Okay, which then equals mu naught I, okay, over 2r. So that's a great application of Biot-Savart. Okay, and our last consideration for our test tomorrow, again, is going to be what if I've got a wire in this direction here and the current's moving in this direction. Okay. Now, of course, using the thumb rule, okay, that means we're going to have dots of magnetic field pointing in this direction like this. Okay. So let's say the length from here is, I'll draw a double arrow here. Let's call this A. And then from here all the way to there, let's call that B. And then this is length L here. Okay, so we're in a situation where we have a differential flux. So let's say the current, of course, is di dt. The current in this wire, okay, is. But just a reminder, we do need to get our differential flux, okay, going, okay, through our rectangle here. All right. Now, to do that, we have to remember the magnetic field generated by this thing is caused by B equals mu naught I over 2 pi r. And our r, I'll draw this in green maybe, our r is going in this direction here. This is our r as we're getting farther and farther away from it. Okay, so then if we look at this, we need a differential area here. Okay, so we have length L in this direction, and in this direction here, we're going to have a dr. So the area is going to be a dA for this. Is actually length L times dr. Okay, so remember our equation for flux is BA cosine theta. Now our theta in this case will be 0 for all of those. Okay, so I'm going to plug numbers or letters into this equation here then. So for B, we've got mu naught I over 2 pi r. And then for area, we actually have L dr. Okay, and this is actually then a differential flux. Okay, because this LDR is our area and mu naught I over 2 pi r is our function of the magnetic field caused by the wire. Okay, so to get my flux then, my flux magnetic, that's going to equal mu naught I over 2 pi. I'm going to take the integral from A to B, and I believe that's how I have this set up. Yep, A to B. And I'll just have dr over r. And that, of course, becomes the natural log. So our flux magnetic equals mu naught I over 2 pi natural log, okay, of r. Okay, and we're doing the definite integral from B to A. Continuing with this then, we end up with mu naught I over 2 pi times the natural log of B over A. And that, of course, is our flux magnetic. Now, to get E for this, E, of course, we have to have the derivative of this right here. So we're going to then discover that it's the derivative of this with respect to time of this whole thing, which is mu naught I over 2 pi natural log of B over A. Okay, well, what's changing in this is I. So E in this case is going to equal mu naught over 2 pi natural log of B over A times di dt. And that will be our E value there, okay, for that. Okay, and then just, correcting something that I forgot to keep continuing, we do need length L in there. So I'm going to put L in our positions here, and we'll go back up there too, because there's supposed to be a length L also for our area. So I'm just fixing that really quickly for all of these situations here. because remember it's a differential area. So there was my L right there that I dropped, but I'm just putting back right now. So that's our final answer. And that's a good review for our concepts for tomorrow's test.